Okay. Yeah. So essentially, when Somnatha asked me to give a talk here in MATLAB, and that has to be something which is not being studied in our course, I was in great trouble because, truly speaking, what I know is what we have done in statistics 1 at max probability 1. Okay. So with that only, so far I was doing good, but then Somnatha created this lot of trouble in my life, and I tried to find out something which can be new to me. So that's the first thing. Okay, then only I can talk. Okay, so I researched several things, and what I found out that okay, so this is something like this name is catchy, this spatial statistics. So I tried to see that what these things are and what it is, and believe me, I started reading it, and then I got extremely disappointed because of my limited knowledge, not because this is bogus, but because of my limited knowledge. And as this will go, you will understand why I am saying that. I got extremely disappointed. So, as statistics, all of you know that it deals with data. So, therefore, we start with the data. Okay. So, what is it? What is this data looks like? Okay, so that's just automatically comes. I don't know. So it's a data in province of Spain. So this is on brain cancer. So this is a particular data, and this province, this Navarre, so it's being divided into 40 health districts. Okay, and for each of this district, so there is something called SMR, which is standardized morbidity ratio. So, which is being calculated by a person named Ugarte in 2006. So, he analyzed this data. Okay. So, not only he, so there were a couple of more. Okay. So, that's cut there. Anyway, so that was the data that was dealt with by these persons, and I looked at this data. Okay. And so what you have? So you have essentially 40 districts, and corresponding to each district, you have some rate. Okay, so this morbidity rate, whatever be. So what you do? So as I have learned, so this is okay. So this is good thing that this is available in R. So it's freely available in R, and the data looks like this. So the name, so that goes with these 40 health districts, and the corresponding SMR being reported. So what you do? So what I used to do so whenever I got this data, so it is being told to me that forget about the name. So you cannot use the name. So I forgot about the name. So I have the data. So then what I have done? So I learned histogram. Okay, all of us learned histogram. So that's like my favorite. So I have drawn the histogram. Good. So this histogram is a bit tricky because see that this data is working with or dealing with this morbidity ratio. So there are something which is higher, like 4 to 5 and 5 to 6. So there are some numbers present there. So which should be OD, right? Because this is this particular data is talked about the morbidity. Okay, so then I thought, no, not only histogram that I have learned, I also have learned box plot. Okay, you also have learned box plot, statistics 1. So that's only I know, right? At that point, at least I knew, yes. That's my suspicious, what I have thought of, that is correct. So there are 2 data points, at least I can see, they are lying outside this line, right? So horizontal line. So these 2 are outliers. Okay. So I understand this data set are having 2 outliers. And for historical reason, outliers were favorite to me. So I was interested. So now I thought that what else? Now as I said that I started looking at the spatial statistics, I looked in R. Okay. So as I said that in R, so there is some tools that so that works with this spatial data as well. So now what I decided to do, so I tried to use those provinces that are being given to us. Okay, and I mapped the same data again. Just to see, this is one thing that I have obtained, that there are 2 points which are up there, but I do not know that corresponding to which region these points are, which can be interesting because we are dealing with the morbidity, so that has to be interesting. So I plotted it. Okay, so that's the first thing that I learned. Okay, so in R, if I give you a spatial structured data and ask it to plot, so it can plot it, and that gives this extra information to me that there are few areas which to be taken care of. Okay, but that was not that big deal. Okay, why? Because okay, so from the earlier picture, from the earlier box plot, I would have traced back that which identity or which index corresponds to those 2 observations, and then I can find out this positions. Okay. At that time, I was not that unhappy. Okay, so I learned something, but not that unhappy. With the histogram and box plot, I can work good. But then I studied, or I took another data set just for my own interest. Okay. So it's a study on 56 counties of Scotland, and this data being studied by this 2 guys, this Clayton and Calder, in 1987. So they worked with this leaf cancer. Okay. And what they have studied, so they tried to get a relationship between this leaf cancer, the number of leaf cancer, and the person and the number of persons who are working outside sun. Okay. So what I have done here, so I have taken a part of this data set, not the entire data set, just the number of persons who are working outside the sun. Okay. So what I have done, so once I have this, okay, so again this is available in R as a free data. So once I have the data, as I said that histogram is one of my favorite things, so I again have drawn this histogram. Okay, so this tells us that there is probably a skewness available in this data, and whatever information that you can get from this histogram, you can have it. But you just have heard that I learned that spatial structure, spatial map, so let's do that here as well. So I have done this. Okay. So fine, so this is the corresponding spatial structure of this Scotland with 56 counties, and this is the spatial distribution of the data set that gives us some idea about the population of these particular counties. Okay, fine. So what is the big deal? So then I thought, let's try to play with this data. What I did, so I just permute this data. So I keep the data fixed. Okay, the numbers are the same. I just permuted the number. So what I have seen next. So now I plot again, make these 2 plots, but in opposite order. First I have done the spatial plot. Okay. So let's try to see this plot and the earlier plot once more. Okay. So please note that 2 points are easy to see. So if you look at these 2 points which are sitting here, so these are probably in this area, in this region, like 3 to 7, most likely this. And then I permuted the same data set and I got this particular spatial structure. Now this changes. Okay. So therefore this spatial distribution clearly it changes. Okay. Where I was, so now my conception has changed about this particular data set if I map it on this map. Okay. Now
you suffer
only the
morbidity, but the ratio you take with respect to the population of that Jew.
So here this is just the percentage of population. So I just permuted the numbers, not the indexes. Indexes corresponding to counties. Okay, so then what? So then let's look at this histogram. I want that. Okay, so let's see what happened to the histogram, and that broke my heart. Okay, so that remains the same. I was like, shit, what I have done so far. So I missed something, right? Definitely I missed.
If you don't change the number, the histogram
It has to be said. But if I said at the beginning that what I knew only histogram. So with the histogram, I could not get this idea that this spatial structure, spatial distribution back in the data set that changed.
We should take the age distribution of all the students whoever is here.
Right.
And then we see.
No, it is not supposed to change, definitely.
No, it's differently, of course, the same. So what is.
Yes. That is so that is the thing.
Same for the histogram or different?
I guess so, because I use the default.
Like second V is the use of the second is which is higher than the first one.
Oh, so here these are automatically generate some bin width, so I just go with it. Okay. I have not done anything with the bin width myself. But what is the point here is that it just remains the same. Okay. So that means with the knowledge of histogram is not going to work. Okay. I was like, as I said, that my heart was broken, and I decided. So what we do? So I understood that it's my fault that I have not studied this earlier when I should have, but someone has to be blamed, right? That's what we always do. So if I cannot do something, so I blame my teacher, my parents, somebody else. So I try to blame someone who I can find out. Now I cannot blame my parents or somebody. So I thought that okay. So these concept of histogram. So from where this comes? That comes from this IID concept, that independent and identical history. That fissure, definitely this fissure made my life so difficult. Okay? So I found somebody, that R.A. Fisher, father of statistics, I blamed him. Okay. So I just, okay, so he did not notice this, and that's why I could not learn all these things. So I was happy for one day, and then I thought that, okay, let's just see whether he has seen that this spatial structure at all in his work. And what I found? I found that in his seminal work, so that's probably the most famous work by Fisher, that is the design of experiment, he knew about this fact. He was very much aware of this spatial structure and spatial distribution. So, you know, my situation is, but anyway, so I tried to understand that how can he know this, and he was employed in this Rothamsted. So this Rothamsted was a very famous agricultural institute at that time, probably one of the first research institute on agricultural statistics. He worked there for this long period of time, 1999 to 1933, and he encountered some data sets. Okay, so yeah, so definitely he was engaged in analyzing agricultural data, but he encountered some data set which is noticed by Mercer, who was also an employee in that particular institute, and he noticed, or he collected this data in 1911. Okay, so how this data is, so data, this is just a sample data from a huge population that he collected. So it's being plotted here. So here, each square, what you have here, so that particular square denotes a plot of size, this 3.30 cross 2.59 Newton. And these colors, so they denote the yield of certain crops. Okay? So it's a field which is being partitioned into several blocks, and then the corresponding yields being taken care of or being recorded. Now Fisher, of course, encountered this kind of data sets, and he has this comment which I was looking for, that the patches which are close, so their yields are similar, more alike than the patches which are apart. Okay, so that means what? That means that Fisher knew about the spatial structure. So you were aware of this spatial, underlying spatial distribution, and he had a solution to it. It's only me who just did not notice this. What was the solution? So his solution was blocking. Okay, so it's a famous design of experiment thing. So it's a blocking, and what it does or what it says, so it says that if you have a spatial variability, that spatial variability is constant within a particular block. That's his underlying assumption. But he had this in his mind. Okay, so that's what I just have written here. So it's a way of doing this blocking. Probably the most simplest spatial model that you study. It's a kind of analysis of variance. So if I just, so that's arbitrary. So if I just consider this columns, each columns, okay, and I try to compare the yields of these columns. So that's essentially the first spatial model at least I encountered in my life. So that's nothing but an analysis of variance. Okay, and the more efficiently you make the blocks, more nicer result you will get. Okay, so anyway, so forget about my disappointment. Then I started looking at the other stuff. So I thought that
What do you mean by blocking?
oh, so let's say that probably the most simplest block. So I just take this particular column as a block. Okay, so there are, let's say, 25 columns. So
you just average it out.
Right.
And get more homogeneous.
right. Okay, so then I searched for other papers, other findings which were there at that time, and what I found is this guy, so this Papadakis. So he had his own idea, and that leads to what we call now is a random field, or sorry, Markov random field. Don't ask me what it is. As I said earlier, that my knowledge is limited to Stat 1, which of course you have not studied about random Markov field. But what it does, so it does something like this. So, or he tried to do is something like this. So he tried to model the average yield of a particular block given the average yield of its neighbors. Now, how this neighbors being defined? So that's a question of spatial statistics. At that time, he defined it somewhere like if two blocks are like one point neighbor, if they have common edge, so he called it to be a neighbor. Okay, so that's probably the trivial thing, but that essentially leads to this Markov random field. Those who know about the Markov random variable, few of you may be knowing that basically it says that the present state or the future just depends on the present. So similar to that. So the yield of a particular block dependent on its neighbor, not anyone else. Okay. So that was like his finding was, or his contribution was. But what we learned from this particular discussion or from this particular introduction, that what this Tobler said. So this Tobler in 1979, so in a geography book, so he mentioned that everything is related to everything else. Probably the near things are more related than the things which are far apart. Okay, so that's essentially being taken as a fundamental law of geography. I don't know, but just this one I know. Okay, so with all of these things, I started looking at the spatial data a little more intensely. So you remember the spatial data just we have seen. So a percentage of populations, the SMR array, which are being given, which are being mapped on a particular map, and yes.
So if you take a spatial data like the previous one, the crop field, the spatial data has more information than the histogram. That's what you are saying to start with, right? And the more information is more required than having, making homogeneous and making it just to the histogram, which doesn't have, which just reduce information or take, which is lesser information. So why is the interest that to reduce the spatial data into some homogeneity and just make histograms? I mean, unless the histogram is useful, because the histogram has less information, it is less useful.
Of course.
So why
Yes, that's the point.
why should you do that? And if you take a spatial data, there is spatial correlations. And the correlations is typically, let us say this data which we are getting from a field or something, you just a AFM, you can get it magnetized data from a sample or any other thing, like the picture of a tree with how much is being filled or
Yes, of course. So
and that has more information. I can actually say that take a picture of a tree from now in the window and just make it blur like a blackboard. Information. So I will be interested on what is there in the tree, not in the blackboard, and why should I be homogenizing it at all?
Absolutely. So that was my fault that I did not pay attention to this spatial structure that were present in the data set. So that's the whole point. In the courses that we teach, mostly we limit ourselves on the IID. So what you say, just the spatial correlation. So that's what we are leading to. Okay. Okay, but that's okay. So that's helpful. Anyway, but that's the whole point, is that if you use histogram, you miss something. Okay, so yeah, so you remember the structure of the data set that we just have seen. Now we are going to see different kinds of data. Okay, so this is a particular data, so it's being collected in the northern part of Italy, where this circles, what you were seeing here. So these are some positions which are prefixed, some stations which are prefixed, and at those positions, the PM10, so which is called the particulate matter 10, so which is being used for the air pollutions and all. So that's being recorded. Okay, so this particular data, as you can see, is different than what we have seen earlier, right? So this is a different kind of data, definitely, right? What we just have seen. Okay, so next, so this is another data set. So this will be, this is a colorful data, and that will be used later as well. So this is a Meuse river. So there is a river which actually flows through several countries of Europe, and this is from a part of the Netherlands. And these dots that you are seeing here, so again, so these are some locations at which the zinc concentration, in fact, yeah, so here, this is the zinc concentrations are being measured. Okay, so this is one, again, this is similar kind of data that we have seen here, right? So these two data sets are similar, but these are different than what we have seen earlier. Okay, so this particular data set is called geostatistical data or point reference data, and this will be our interest for this particular topic. But just to so complete this discussion, so we talk about these two data sets as well. So these are the data sets that we just have seen. Certainly they are different than what we just have seen, and this particular data set is called an aerial data. I will come to the proper definition of this stuff, but just to so understand what these things are. Now these, apart from these two kinds of data, so there are another interesting data set. So this particular data set is being collected in this following manner. So in a forest, a few researchers went for location of pine trees. Okay? Now beforehand, you do not know that whether you will get a pine tree at a particular position. Okay? But here, so therefore, these locations that you see here, so they are random. So they are not fixed. So it is different than what we had earlier. So earlier stations were fixed, PM10 were measured, so PM10 can be taken as random. Okay? So in this case, the locations are random. Now apart from this, what we have taken, so we have considered the width of the this bunk of the tree, so what it is called? Trunk of the tree. Okay, so that's being recorded also, so that's why it's the circles basically denote that whether
The trunk of all trees
or the pine trees that you obtain.
Each point corresponds to one pine tree.
Each point corresponds to one pine tree. And the circle, so as it goes larger, so the width of the trunk gets bigger, and smaller circle denotes the small. Okay. So that's another kind of data, right? So that we have not encountered so far. So we have considered this three kind of data set, and this kind of data set is called point pattern data. Okay, so what this data set is? So that's the location where the crime happened in Chicago. So again, you do not know before the crime happened when or where the crime is going to happen. Okay. So that's another kind of data set, and that's called the point pattern data. We'll come to the formal definitions of all these, not very formal, but some bit of formal definition of this. Okay, but before we do that, what we need, so we understand, as Sam was saying, that there is a spatial correlation. So these are Fisher noted, so the blocks which are closely apart or closed, so they are, yes.
So this covers all the binaries?
Uh,
It's randomly chosen some binary.
No. So of this particular region, so there is a region being fixed.
All the
All the
binaries are
binaries,
covered.
all the
Covered.
binaries.
So the randomness, what you say that the binaries
Locations
occur
occur or not?
Yeah.
So yes. Okay. Yeah. So these interrelation, this interdependence has to be taken care of, right? So some way or the other we have to take care of. So that's one point. The another point was, so which is mostly related to geostatistical data. Given the data set, we would like to predict the observation at a new location. Okay. So these two things, of course, for any statistician, prediction is one of the things that we would like to do. So these two things have to be taken care of. Now, the easiest possible way to do this is to introduce a stochastic process. I'm sorry to introduce this word, but okay, so just assume what this stochastic process is. So the stochastic process is essentially a collection of random variables, okay? You know the random variable is a mapping from a sample space to R, right? So if you have a stochastic process, now it's a mapping from omega comma t to R. Okay, so let's say the omega cross t to R. Okay, so let's say that's my stochastic process is, and what we observe here are not independent observations that we understood. Okay, so histogram is not going to work, as Sam was furious. Why are you listening? Yeah, so we understood that that's not going to be the case. So, what you observe essentially a particular realization of this stochastic process. Okay, so it's a big difference. In case of independent observations, you have several observations, actually lot of observations, not less. But when you assume that you have a realization of a stochastic process, so you just have one single realization of a stochastic process, okay? There is more problem attached to it. You actually don't even observe the complete realization. So what you observe some points at those realizations, okay? So it's a bigger issue than just these histograms and all. So we go with this idea of this stochastic process. We go with the formal definition of these three things that we just have noticed. Okay, as I said, so it's just a collection. Now this collection is indexed by S here because S stands for the location, and this S varies in this script S. Okay. Now what this geostatistical data? Now in geostatistical data, now these three kinds of.
I have a small point. This is actually for spatial processing in geophysics, geological.
Statisticians call this to be spatial process. No, nothing different. So it's just, it is assumed that this S is a subset of R2. So
this is the
that's just the locations.
So what you call T stochastic process is calling it now S.
Right. Yeah. Right. So now in this point reference data, now these three kinds of data sets are being distinguished based on the structure of this script test that we have. Okay. So in geostatistical data, what we assume that this S continuously varies on this capital S or this script test, and this script test is a subset of this R2, and which contains a rectangle with positive volume, so that you can move freely within this S. Okay. So that's what this geostatistical data is. Now what is important, I just repeat here, this the locations are fixed, the sites are fixed, the excess that you observe, so that is random. Okay. Okay, so that's an example. I repeatedly give this example because we are going to come to this particular example again. So that's an example of this geostatistical data, and that as we have seen in the last slide, that we mentioned that this S1 to Sn, so they are fixed, but this x S1 to x Sn, so they are some random variables. In this case, these are just concentration of genes. Okay, so the other data set that you have seen,
And the sequence is arbitrary. The sequence is arbitrary. I mean,
S1, S2, Sn, so this particular sequence is arbitrary.
yes. So which one you call S1? Like the first one here it is S1, the other one is S2.
That doesn't matter. That doesn't matter. Okay, so now what is aerial data? So the data that you have seen earlier, where this map being partitioned. So exactly that is what being done. So this, you have a map, you have a region which are being partitioned into separate blocks, and here this S is essentially a fixed collection of countably many points or spatial points. Okay, so they are characterized by something in order.
But sorry, but in a actual, if you are going to take care of the special property, special property, then there is a locality in the space, right? I mean, you know, which one is close to which point, there is a locality in the space, and this one doesn't take further about that.
This aerial data does in its own way, like the which blocks are near to which other blocks. Yeah, so that's just looking the data set that you have seen earlier. Again, what is important here, that this S1 to Sn now denotes the blocks, but these are fixed. Okay, so there is nothing more randomness present here, but what you observe, what is measured is definitely random. Okay, yeah, but these are not really interest to us. We are mainly focused with this, but let us finish this. So what is point pattern data? So in this point pattern data, as we understand, as we discussed, that this S1, S2, Sn, so they are random. Essentially what we are saying is that strip test is a random set. Now you will ask what this random set is. Okay, so this random set is a mapping, is a measurable mapping from a probability space to a measure space on the subsets of R2. Don't worry about it. So I just, before I come here, I just marked up this one. So don't worry about it. That's why I was like figure that I will tell this. Don't worry about this. So what you mean by this? Now realization to realization, earlier the X was varying. Now this S will vary. So that's okay. Okay, so just an example here, as I just given this example earlier. No, wherever Somnata will say that, okay, enough, we'll stop.
So this, when you take this S, so the variability, if what you call S as a set, can only be the number of permutations, right? All possible permutations of S, because those are the things. So can you define a Markov process in this one again? Like, you know,
So
it's a
this
design process, which is stochastic process, a Markov process on this space, which is all permutations of S.
Right, I mean, it's not that easy to do it here on this point process. So there is a Ripley in 1977 have done this work, and that is like very not very different but very difficult than just a stochastic process. So this is called a point process, and that covers not only a random variable, that can cover a random set and a larger set than just a random variable. So we don't go here because again, so I just repeatedly.
I told you to keep quiet.
No, it's fine. It's absolutely fine. I mean, I'm not in a hurry. I'm not doing any course or something. Yeah, this just makes this talk more interactive. It's good. Okay, so come back to the spatial data, or rather geostatistical data that we really would like to talk about. Just before talking about this, I just would like to say a few things. So there is a guy called Macaron. Okay, so he has 3 consecutive papers in in 1960s who essentially built all these theories of this point reference data. Similarly, in 1974, Besag, so he developed the complete theory for this aerial data and for this point pattern data, as I used to say, that Ripley in 1977 did most of the work, okay, the fundamental works. Okay, so we go with the geostatistical data. And whenever you go with the geostatistical data, what you do, the first thing that you do some exploratory data analysis that we already have done, right? So essentially we made this spatial plot, okay? Now what you see, so as I earlier mentioned, this is just a part of the river in Netherlands, and these are just zinc concentrations that is being measured at these particular locations, okay? What we observe, if you observe this closely, this data set, so these concentrations seems like decreasing as my distance from the river increases, okay? And the guy who did this analysis, so I forgot his name, so he had done this in 1996 most probably. So he noticed that, he collected this data set and he noticed that, and then he tried to analyze this, okay. So he only mentioned that, that's why I noticed it. So then what you do? So you see that you have this gene concentration and you obtain this information that as my distance is increasing, so this gene concentration is decreasing. I was like very excited, okay, linear model, so linear regression, so let's do linear regression. So I plotted this distance and the log of the gene concentration. Yes, there is a negative correlation, nice negative correlation. So all of us know this simple linear regression, okay. So I did that, and what I do next? Now, what you do next after you fit a simple linear regression? So you analyze the error, right? You try to know that whether the fit is good or not. Now, when you analyze the error, so then I use again what I just have learned, that is the spatial plotting. That's the only thing I could learn from this all these times. So I have this I have the error, I have the corresponding spatial information, I plotted it. I plotted two things, the fitted values and the residuals. Okay, so this left one is the fitted value, the right one is the residual. Okay, so what you observe, yes, truly the fitted values take the major variability of the data, so it explains major variability of the data, but we cannot really say that from this one that these errors are spatially uncorrelated.
The color is changed. I'm sorry.
Sorry.
So there is a black point there. That color is become pink here. These black ones. And on the right hand side, those are become
So these are the fitted values, and you have the observed values. Now you subtract that, so you get the residuals. And I just plotted it on the spatial. You have the spatial location, so I have just plotted. Okay, but what is important to note that, okay, so these are not really spatially completely uncorrelated. So these points, these blue points, as you can see, so they try to so be together. And
Ideally, what should that one have been?
I mean, it should not observe any pattern as such, right? So if they are spatially uncorrelated.
So a random color.
A random occurrence of these colors you should have observed. Okay, so essentially this is being written here. So what my intuition suggests that, okay, so some more analysis of these spatial data is required. Now to do that, I just hold for a second here. We'll come back to this data set again. We need some part from this stationarity. Okay, we understand that there is a correlation. So correlation has to be taken care of, as Sam was mentioning. But I cannot just leave the correlation completely arbitrary, because it can be many different ways it can vary. Okay, some way I have to restrict, And one way to do that is to introduce this stationarity. Now there are a couple of stationarity present. Which one, this particular, in this talk, what I am going to tell about. So it's about the weak stationarity and intrinsic stationarity that I will come later. Now, of course, there is a strong stationarity, so I'm not going into that particular part. Now, what this weak stationarity is telling us. Now, this is a property of the process. So, this says that the expectation of xs will be constant. The expected value will be the same for every s. So, that's the first thing. The next one, that's the crucial one. So, it says that if I take the covariance between xsi and xsj, so then it will be a function of the distance between this s1 or si and sj, or not the distance but the difference between this s1 or si and sj. Okay, that means what? That means it does not, if my si minus sj is same as sk minus sn, so then this will remain the same.
The locality is not taken care of, this will not hold because S1, S2, if it is here and here, the value is 3, and if S1 is here, S2 is there, then value is 7. For the same covariance, what you get, if sometimes you get C7 and sometimes you get C90, 29.
Yeah,
so the locality has to be taken care of, the ordering in S has to be taken care of somehow. Otherwise, the distance will not have a meaning.
No, so this S1, so that's like what you were, I thought what you were asking, that what you were denoting. But it has a spatial location, so it has a latitude and longitude, right? So it, I mean, those cannot be, I mean, we are here in Kolkata, so that cannot be London, right? Although our CM does. Absolutely. So these are like the locations, the latitude and the longitude. Yes. Okay. Yes. So that's called stationarity, and there is a special structure, a further special structure. So if this covariance is the function of the distance, okay, so the norm of it, so then this particular function is called isotropic. So the covariance function is called isotropic covariance function. Mostly we will be dealing with this isotropic covariance function just because it is easy to deal with for today. So we are just going to deal with this. Okay, so now there are a couple of interesting properties of this covariance functions. So these are being listed here. Among all these three properties, the second one is quite interesting. So what it says, so this function has to be positive semi-definite. So what does it mean? So it means that if I take any n bigger than or equal to 1 and any real numbers a1 to an, then the double summation aiaj c of si minus sj will be bigger than or equal to 0. Essentially, if I just take a finite number of locations, let's say, the corresponding matrix will be positive definite matrix or positive semi-definite matrix. Okay, so that's what it says. So why I'm saying that this is interesting? Okay, so there is again a story here. See, I mean, Onivan several times told me that please do probability 2. But I always used to say that, okay, see, I am an applied person, so I don't care about all these things. But the problem is that even when I looked at this particular stuff, so I need something from that particular course. Those who think that that course is for a very pure stuff, that's not really true. Why I'm saying this, the reason is interesting to know that if I have a positive semi-definite function, see, now I say that I have a covariance function which is stationary, which will be positive semi-definite. Okay? Now it says if I take any function which is positive semi-definite, I can then relate to a stochastic process whose covariance function is the positive semi-definite function that you work with. That's the strength of this particular property, and this particular theorem is essentially the Bochner's theorem. Okay, and that's probability 2, and you know, Anyway, so we go a little bit further. We relax the stationarity a bit further. I will say why we are relaxing this. So again, this method. So I talked about this particular person. So he introduced this particular notion. Okay. So what it says, the constant mean is there. So the expectation of xi minus xj is 0. But it says about the variance or the expected squared of this difference. So that is a function of the difference between Sj and Si. So that is what these assumptions of this intrinsic stationarity by that we mean. Now you can ask that why I am keeping this 2 here. So you will see that why I am keeping this 2 here, why I am not denoting this one as gamma of h, but I am just purposefully putting this as 2 times gamma of Sj minus Si, and this one, this expectation of Si minus Sj whole squared, so this one is called variogram, and this gamma, this part, apart from this 2, so this is called a semi-variogram. Okay, so in spatial statistics, people mostly work with semi-variogram instead of co-variogram. In time series, we mostly work with autocorrelation instead of this particular version. Okay, now these, if I have a process with this property, so that will be intrinsic stationarity. That will be an intrinsic stationary process. These things I mentioned. Okay, so again, if this happens, that means if this gamma of h is just a function of the distance, so then this particular function or this semi-variogram is called isotropic semi-variogram, like the way we have defined the co-variogram. Okay, so there are certain properties as well. So these are, I mean, there are some other properties as well, but these things again is important. This conditionally negative. Now, what does this conditionally negative definite mean? So it means that again the same structure for every n bigger than or equal to 1. If summation of ai is equal to 0, then the double sum, what we have talked about, this aiaj times gamma si minus sj is less than or equal to 0. Now from where this just comes up? For the covariance, it's easy to understand because that's nothing but the variance of the A transpose X. Okay, so that's why it has to be bigger than or equal to 0. So from where this just comes up, we'll come to this. If I could finish the talk, then I will come to this because that comes as a part of kriging. So nothing comes from sky, so this also comes from kriging. That is the last part of my talk.
So, could you just give an example of data sets which satisfy these kind of problems?
It's very difficult to so check that whether these things are satisfied. But there are certain sufficient conditions available using which you can check whether these conditions are being satisfied. Yes, so those are there, but those are mostly after you fit a particular covariagram to a data set. We come to not really we come to the sufficient conditions, but we'll discuss about how to fit a model covariagram or a parametric covariagram to a non-parametric one. Okay, yeah, just to remind us that this gamma h, what we just have talked about, this intrinsicity, so these things is particularly a property of the difference. So it is nothing to do with the original process. It can happen that the original process does not have any moment, okay, but still it can be intrinsic stationary. So just I have given one example here. More disappointing thing is, or discomforting thing is this. We may have this xs minus xs dash as a proper density. Even we may have the conditional density of xs and given xs dash is proper. Conditional density of xs dash and xs given xs is proper, but the joint density of xs and x S dash is not proper. So there are examples available with that, and that's a problem. So that's a very big problem. Just to remind us, if you are working with intrinsic stationary distributions, so you can only talk about the difference. Okay, provided something happened. Yes. Proper density meaning that you integrate and get it to be 1 or finite. So that is, you need the finiteness so that you can scale it and get back the density. Okay. Okay. Fine. So then what to do? So as he already posed a question that how do you know that a particular data fits some certain problem?
Who asked this question? Yeah, I want to add one thing. This property is telling intentionally the reason is that there are distribution functions which does not add up to 1. If infinity is not 1, it is less than 1, and that is recorded in different places. That's why he is specifically telling that it's proper. This kind of distribution function or corresponding density will not work with.
So, and in fact, the example here is very simple. So if you just take e to the power minus xs minus xs dash whole square as the joint density of xs and xs dash, so that will work. Okay. So that will like satisfy these conditions. Okay. So yeah, as he was asking this question that how do you fit, how do you justify or verify the conditions that we were giving. So to answer that, towards that, not completely, we will do something. So we will come up with different kind of radiogram functions. Now why I'm coming up with these different types of radiogram functions? Because all of you have done certain distributions, right? So you have done gamma distribution, you have done normal distributions, so different beta distributions, uniform distributions. So those distributions you studied why? Because you would like to fit a data to that particular distribution to get more information out of it. What this data is saying, so you want something more beyond that. Exactly same way. So we pose or we give certain amount of, or like a list of couple of this gamma of h, okay? And then using the data, we will find out what the gamma of h is, like a non-parametric version of this, and then try to see that which fits well. So it's just like the data set that you have analyzed in Stat 1 course. Okay, so the first, probably the easiest one is to talk about this one. So this is a linear semi-radiogram, so which of course looks like this, but you can see that there is something interesting here. We understand in the gamma, in the definition of gamma of 0 has to be 0 because expectation of x minus x of s plus h, right? So that has to be 0 if h is equal to 0. But here we see something here. So of course at 0 it has to be 0, but it is not right continuous, right? So if I go from this direction, so there is a jump, okay? And that jump is being characterized by this eta square. Now what this eta square is, we call it to be nugget. Now from where, from all of a sudden, where this comes up? Okay. So the answer to this is, see, the statisticians love error. Absolutely they love error, although not in answer script, but generally we love error. Okay. So what we assume, so we assume that we do not only observe this xs, okay? So this xs is
The sigma square here is variance of this data?
sigma square, we call it to be partial c, so it's just a parameter which is a positive parameter. Okay, let's take it that. Okay. Okay, so what we assume here, so we are assuming that we are observing a spatial process, right? A realization to it, okay? But that's what I say, that we statisticians love error, so we assume that there is a measurement error attached with it. So not only there is a, so that measurement error is nothing to do with the spatial variability. So you just add error. So instead of observing xs, so we assume that we actually observe ys, which is something like this, and this epsilon s is independent of this xs, and these are essentially IID. So they're nothing to do with the spatial dependence. And they have, let's say, the expectation of epsilon is 0, and the variance of epsilon is sigma, your tau square for every s. Okay, so that's the measurement error. Now, towards the big
Simply epsilon, right?
epsilon, simply epsilon. But you have, like, if I have observations, like you have S1, S2,
Right, for that one.
Sn, so you have epsilon 1, epsilon. So this is just to differentiate between the V that I just have added to the Cauchy. Okay, so right. So this epsilon is that particular. Now, towards the beginning of this lecture, if you look at the slide, which I did not mention, that we are interested in the larger variability as well as the smaller variability when you try to work with this geostatistical data. That smaller variability is taken care of by this particular epsilon. So it's nothing to do with the spatial structure as such. Okay, so that's what from where this tau square has been arrived, and that's called a nugget. And in this particular case, as you can see that, oh, I forgot to mention something about the relationship between this gamma h and ch. Sorry, so that I should have mentioned. So I have to go back. So if I have a stationary process, so then this gamma h can be obtained as C0 minus C of h. Okay, so provided you have a stationary process. So then, given a stationary process, given a covariance function, so I can come back to this gamma h. On the other hand, if I just give you gamma h, it's not that trivial. Only stationarity will not lead to ch, so you need something else. Now, something else has a name, but for time being, if we just assume that this ch goes to 0 as my norm of h goes to infinity, which is not a very unusual assumption. So what you are assuming that as my distance are getting apart, my correlation reduces. Okay, so if we just do that, so then I can get back this ch, right? So this ch as the limit of let's say gamma u, where this mod of u goes to infinity, minus this gamma h, right? So in that case, if that happens, that ch goes to 0 as mod h goes to infinity, so in that case I can trace back this c of h, and that property or what we need is called ergodicity, not going into that. Okay, so here the point is why I'm doing this. So because in this particular case, we can see as my norm of h goes to infinity, so this gamma h goes to infinity, so that really does not satisfy that. So that means I cannot really get back a covariance function from here. Okay, so that's a drawback, and people generally do not use this. Okay, so another interesting semi-variogram function is the spherical one. Now this one, apart from this nugget, so there are two other things. So one is called this 1 by 5, so which is called the range, and as you can see that as my mod h goes to infinity, so this converges to this tau square plus sigma square. So this tau square plus sigma square is called the C. Okay, as you can understand from the picture. Okay, so after this range, so what we call as 1 by 5, so it reaches this C. Okay, so and if I subtract this tau square from the seal, so what you get as the partial seal, in this case that is the sigma square. Okay, so nothing can be completed using exponential, without mentioning exponential and Gaussian, which we are going to do. So this exponential is important in a sense that the spherical one that we just have defined, so this is not a valid variogram if I go beyond a fourth dimension, which we generally do not require, but still that's a drawback mathematically. But for this exponential one, so I can go to any other dimension, but what is important here that there is no range as such, although the C exists, which is again tau square plus sigma square, but there is the range is infinity, and in that particular case we work with the effective range instead of range. That means you draw a epsilon, you fix a epsilon, and you see that after which point it enters within the band of this epsilon. That's the exponential semi-variogram picture of this. So as I said that nothing can be completed without Gaussian. Now this Gaussian has its own beauty in a sense that if I have a Gaussian semi-variogram, I can have a corresponding co-variogram as well, and importantly the corresponding process is infinitely smooth. Now I'm not going into the details of what we mean by a process to be infinitely smooth, but that's what the beauty of this Gaussian variogram is. That's a drawback as well as beauty, because in reality you may not have an infinitely smooth process present here. So that's a picture of this. I know I'm running out of time. Yes.
So domains can be any question. Domains can be any kind of function, right? You are talking about some specific functions because these are the universal functions. These are only universal functions of this
So
kind.
there are many different kinds of
It
functions.
can be any function.
Huh?
Domains can
No,
be any function.
no, it has to satisfy that conditionally negative derivatives.
No, in reality, you can measure.
So I will come to the data set and then we'll see that how I can measure.
So right now, when you measure, will it fit into one of these forms, or there can be any other form?
No, of course it can fit to any other form that I don't know. So that we never know that which it fits. Right? So we just try to be close as possible. Okay, so yeah, I don't know how much more time can I take. 15 minutes? Okay. Okay, so this is the last example of this domain. I'm not going to bore you too much, but this is a very important example which is due to Matter, and he actually revolutionized this particular field by introducing this actually covariance function or the covariogram instead of the semi-variogram, which is derived from that. So why it is interesting? So of course it involves this Bessel's functions and all that k nu what we have written. So this is a Bessel function of second kind. It has different integrity, or rather different complexity mathematically. There is a person called Stein. So he devoted his book on this Mattern function. Okay, so that book is being published in 1999, and he has a comment in that book towards the end. So if you have a data and you want to fit a variogram or covariogram, use Mattern. So he loved that Mattern so much. The reason is this mu that we have here. So it controls the smoothness of the process. Okay, so it can be infinitely smooth if we take this mu to infinity, and it can be very less smooth if we choose a very small value of mu. So it has a big range which can be used for different kind of processes. That's the reason basically, and that's just an example of this one. Okay, so enough on these things. Of course, there are many more, but we'll be happy with these 4 or 5 things which mostly we use. Okay, and in fact, if we take this mu to infinity, so it boils down to the Gaussian semi-variable. Okay, so okay, fine. So data again. That means with these discussion, I go back to the mu's data that we were talking about, the log of concentration of the gene. Okay. Now, as Sarah was asking that given a data, how do you estimate your domain? That's a very natural question. So that is the first thing that you do. Given a data, I know how can I estimate a mean. So therefore, I should know how can I estimate this. So let us just think about or recall the definition of this gamma h, or 2 times gamma h. So 2 times gamma h was the expectation of x of s plus h minus xs squared of x. Right? So that's what it is. So we would like to estimate it. How do you estimate it? So very simple. So you fix a distance d, where you have the data set, right, and see which of the observations which are at a distance d, and take the average, difference them, take the average. Okay, so that's what you do here. So you have this xi minus xj. You took those si and sj such that this nd is such that this si minus sj, the distance of this is equal to d. That's a natural thing, but there is a problem. The problem is you may not have any point which has just this satisfying this particular property, right? So therefore you have to deal with this. So how do you deal with this? You partition the complete distance into separate parts, and what you do is you replace this nd, what you have here, by this ndk. Now what this ndk is, so you look for those si minus sj, pr si sj, such that this distance lying between this. So this is similar to the histogram that we have for the special form of the histogram. Okay, so we just do this and estimate this. We have the Muse data, apply this and get the estimate. So that's the estimate that we observe. So in this direction, x-axis, we have the distance. In this direction, you have the semivariance or the semivariate. So there are certain properties of this. So these are consistent, but not necessarily unbiased. Okay, so that's estimated semivariogram from the data set that we have. Now I have listed many examples of semivariogram, and I try to fit one. So which is not the best one to fit, but I did one. So which I did it here is the spherical semivariogram. Okay, so you just see that there is increasing and then it stables down. So we could have used the exponential Gaussian, but I just decided to use the spherical one. Okay, but the point is I fitted the spherical one, but how do I calculate the coefficients? I have the coefficients, this tau squared, sigma squared. So these things have to be estimated, right? So how can I estimate this? So there are many methods available. So if I assume distribution attached to it, I have used maximum likelihood or estimated maximum likelihood, or generalized using like generalized list square. So there are different methods available. Which we use here is the weighted least square technique, where this wk, so these weights are being taken as proportional to the number of observations present in ndk. Okay. Now why we are doing this? There is a reason for that. Now I will come about this person Cressy towards the end of this talk. So Cressy in 1985 proved the result where he showed that if you take the weights to be proportional to the ndk, the cardinality of ndk, so that gives a very close approximation to the weighted least square again when the weights are being taken as the inverse of the variance. Okay, so that's why this is being taken as the weights are being taken as the proportional to the number of observations being present. Okay. Anyway, so without going into that detail, so I fitted this data. As I say that this is certainly not the best fit. Probably there is another covariogram or variogram which I have not mentioned, is called wave variogram, that could have fit better.
How did you get tau square and sigma?
Yeah, so this one minimize. So it's a minimization problem. So minimize this to get those estimates. Okay. Anyway,
What is sigma k? Like what is it? K. There is no sigma here. So
no, there is no sigma here, but sigma is present here. No? So because so that's the fitted one. Cap is the fitted one, or hat is the fitted one, and that's okay. Now to the last part of this. So fine. Yes. Why we are fitting this? We are fitting this we are putting a covariogram or variogram attached to this data because I want to predict at a certain location which is not present in the data. That was my idea. Now just with this gamma hat, so which are based on the observations that are given, so it's not good enough. That's why I fit it. So I assume that this process being obtained from this particular variogram, and I will use that to predict the observation at a unknown location, let's say S0. Okay. Now what is the task? So just I repeat the task. Task is this: I have given this set of observations and I would like to predict this S of S0 at an unknown location, or at a new location rather, which I denote as S0. Okay. So now this one, this prediction, this spatial prediction is called kriging. Now why this is called kriging? Because again, so this is to honor a particular person called Krieg. So who first published the paper where he used the concept of this spatial prediction for mining. So he was working with the data which relates to mining, and Matharon, to honor this Krieg, used this spatial prediction as kriging. Okay. Now there are three different, or rather many different kinds of kriging, and we are going to talk about these three of them. So which is like ordinary kriging, simple kriging, and universal kriging. Mostly we'll be interested, or we'll be focusing on this, but I would like to talk about this ordinary kriging to relate you with the conditionally negative kriging. I did not forward that, okay? Because that just turns out, I mean, that seems to be coming from out of sky, but that's not. So what is this ordinary kriging? So this ordinary kriging is predicted using a linear combination of these elements of x. Okay, so these are being present. That's the natural thing that you do, right? So you have x1 to xn as your observation. You want to predict a new observation, so you take a linear combination of them and see that, try to get the coefficient of those linear combination to get the best prediction, right? So that's essentially we do a lot in practice. So what you do, so this is the linear combination, I write down that. So I need certain properties to be satisfied, right? So any arbitrary linear combination of course will not work. So what are the minimum thing that you can expect? So you expect that the expected value of the difference between this xs and this guy should be 0. At least they should not differ in their expectation, right? So this is the first thing that you require, and then what you would like to do, so you would like to minimize this error square, okay, expected error square. That's a very usual technique that we would like to do. Okay, so I just rewrite this a bit, so whatever is being given here. So I write down a0 to be equal to 1 and this ai to be equal to minus li. Okay, so what you observe here, so you observe that the summation of ai has to be equal to 0 because of this condition that is required, right? Okay, now, and what you were trying to do, you were trying to minimize this guy with this particular condition. And what you can show that if you assume intrinsic stationarity, so then this guy is nothing but the negative of this quantity that we have mentioned, okay? And from there we have arrived at conditionally negative, okay? So this condition is not coming from nowhere, so it has a purpose to come out. Okay, so that's just
The factor of 2 you started at the beginning is helpful here because you don't have that factor.
So that exactly. Yes. Yes, so now what you do, so I just come back or go back to the original formulation and we minimize this with respect to L, right? So you differentiate equal to 0, solve for it. So that's the usual technique and that is what you do. But unfortunately, if you do that, it will depend on this gamma that you have seen here, but this gamma depends on sigma, tau, etc. So therefore those have to be estimated and those estimates have to be used, and hence these L depends on the data and that is not anymore a linear estimate, right? Okay, Now I go to the universal kriging. Now this universal kriging is helpful because it also considers if you have a covariate information. Now in case of news data, remember that we have a covariate information, that is the distance between the river and the point. Okay, so that covariance information is present with that. Now what you have assuming here, so we are assuming that, let's say these are my covariates, and what you do, so those who have learned linear model a bit or linear regression, so it's very close. So we just use this particular one, this particular formulation to predict a new x, right? So x at S0, a new location. Okay, so I purposefully use this normality because that again always help, normality always help. But let me ask you this question. So suppose this x1 to xn being given to you and you would like to predict at x at S0, sorry, you would like to predict x at S0. What will be the natural predictor that you would like to give? So you have a data set x1 to xn and you would like to predict at a particular point and you want a predictor for that. So what would be your natural predictor? Conditional expectation, right? So you have the expectation and you have the data being available, so use that data and get the expectation of that. So you do that, but that normality is helpful here because, okay, so this sigma, sorry, so this sigma is the structure that we have, like already have discussed about it. Anyway, so this is what is important here, that if we assume this normality, this conditional expectation has a nice form, okay? So this one I obtained that, but the problem here, again, this beta is not known. Gamma is essentially a vector containing the covariance between S0 and XL, so these are not known, right? So they have to be estimated. Now there are methods to estimate that. Anyway, so these things are being already estimated using the weighted least square, but this beta has to be estimated, sorry. And we estimate this, I don't go into the details of this, we estimate this using our linear model knowledge, and we estimate the corresponding sigma hat, and then we predict, okay? So then we have the prediction as this, right? And the corresponding prediction error variance is being given, so it's not that important right now. So we are done, right? So we obtained a prediction at a new location, it's not. Are we done here? No, of course we will check it. Yes, definitely we will check it. But is the process completed? Not really, because you may not know Z of S0. S0 is a new location. You have the data set, you have the locations, you measure the distance, you measure the gene concentration, but now I come up with a new location. I have not measured the distance from the river, so I have to calculate that as well, right? So, yes, I know we are in that stage, but still this is not known, so we have to figure that out, and that helps. So this iterated process helps. So you can notice that this x S0 hat, so that can be written as lambda transpose x, where this lambda is this, and if I pre-multiply this lambda with z transpose, so that will give back me to this z of S0. Then we just iterate meaning that you start with a initial value of z of S0, you obtain the lambda naught, you obtain the corresponding x of S0, and then using that you again obtain this z S0 using this particular form. Okay, so you iterate that and you stop when this process converges. So that ends the story essentially, but let's go back to the picture here. So we just use this formulation, whatever we have studied so far, on this particular data, and that's what my prediction looks like. Okay, so it's being predicted completely on this particular plane of this river. Okay. Now, how this prediction is, I have not done any further analysis, which, as Sam mentioned, that we should have, but I just have given the corresponding data sets that are being observed here. So you can see that it's pretty close, and with it goes with the assumption that the observations which are close to the river, so they are higher than the observations which are far apart. Okay, so that's pretty much all, and these are three very important references if you got any interest in this spatial statistics. So you may look at these three books, which are very nice. Especially, I would recommend this book by Tracy, and he had done a lot of theoretical contribution to this. Okay, so
Sorry. Oh, it's a nice, interesting talk. I like it.
thank you.